In the next part, we will learn how to create the mesh and apply boundary conditions and applying loads. In this problem, however, we want to simulate a tensile test which is displacement controlled, which means no force load would be given. So we would apply two different boundary conditions in the two uh, different regions, and that would eventually cause the specimen to elongate. নিউ পার্ট ক্রিয়েট করেছো, ওই সব করে বডিকে অ্যাড করে পার্ট ক্রিয়েট করাটা করেছো? ঠিক আছে। হুম হুম, হ্যাঁ থাকবে, এক সেকেন্ড। Okay, now we are in the mechanical window. So earlier we are in the design modeler window, and rest of the job, so apart from engineering data and geometry, rest of the job would be done uh, within the mechanical window. So in a finite element analysis, there are pre-processing, there is solution and post-processing. So solution is basically this, the post-processing is basically the results segment, okay, and anything that comes before solution is pre-processing. So providing the material parameters or creating the geometry uh, or even creating a mesh or applying boundary conditions or loads all come under the category of pre-processing. Out of this, the two pre-processing options, that is providing the material properties and creating the geometry, they have separate environments. So you will have to open separate windows. However, for rest of the pre-processing and post-processing and solution options, you get to do in a single window, and that is the mechanical window. So currently we are in the mechanical window. So as it says, Ansys mechanical. And here we'll have to create the mesh and apply boundary conditions, and if needed we will have to create different coordinate systems as well. Sometimes in a problems which have this kind of axisymmetric geometry and axisymmetric loading, it helps to have a cylindrical coordinate system while trying to apply the boundary conditions. Okay, probably we'll create a cylindrical boundary condition, so that we'll know when we go into the further details. Right now there is only one material, and that is the structural steel. If we create a new material, okay, that detail would be updated over here. It shows a lot of information about the material, including the SN curve and whatnot. But all of that is not important for us today, because we are not doing a fatigue analysis. We are doing a simple uniaxial tensile loading solution, such as a tensile test, hence the tensile specimen. So all of this information is irrelevant to us, including thermal conductivity and coefficient of thermal expansion, if there is any. The reason they are insignificant, irrelevant, is we are going to consider that we are conducting the experiment in the room temperature, and there is no temperature variation while the experiment takes place, which means no thermal strain should be included in our analysis. Okay, so the only parameter that matters are the Young's modulus and Poisson's ratio. These are the only two parameters that are relevant to us for this simulation. You would see the bulk and shear modulus, they are simply derivatives of Young's modulus and Poisson's ratio. You can look in your strength of materials textbook or any theory of elasticity textbook, or even over the internet, you will find relations for bulk modulus and shear modulus for a linear elastic isotropic material. Now we say this in a single breath, linear elastic and isotropic material. These are three separate things. Being a linear material, being an elastic material, and being an isotropic material are separate things. Okay, when all of these come together, you only need two parameters to represent the material behavior. Okay, so that's what that is there. The isotropic second coefficient of thermal expansion is also irrelevant to us. Anything else is also irrelevant to us. The compressive yield stress brings no significance. When we use the elastoplastic properties, when you when we would be using the plastic properties, we'll separately calculate the yield stress and we'll separately use that in the respective plastic model. For example, if we use Chaboche kinematic hardening, we'll incorporate the yield stress over there. So right now the yield stress that you see is of no significance to us, and if you wish, you can actually delete them. You can actually delete them from the engineering data itself. Okay, so apart from anything apart from the isotropic elasticity, you can delete. Okay, so including field variables, I don't know what they are. There are none. Density also we would not need, because we do not have any gravitational or acceleration load, that is any kind of inertial load. We can delete the strain life parameter, we can delete the SN curve. The tensile strength also no importance to us. Same with the compressive yield strength. Tensile ultimate strength also irrelevant. Compressive ultimate strength irrelevant. Nothing is required, only isotropic elasticity is required in engineering data. And all the changes that I made in the material properties is not reflected in the mechanical window until and unless I do this, go to materials and do a refresh material, and immediately all the other properties are gone, although I see some of the thermal properties there. Basically, when we have our material data today, we are not going to use any material data, but once we have ours, we'll fit material parameters from there, and including the Young's modulus and Poisson's ratio we can assume, okay, something between 0.2 and 0.3. So the thing is, we would not be needing the data that is there over here as well. We'll create a separate material for us. For example, if we conduct the experiment on 304 stainless steel, we'll use the properties of 304 stainless steel and we'll manually feed those parameters. Okay, so that we would be doing. Okay, but for the time being, we'll leave it as it is. Okay, for the time being, we leave it as it is, because in order to run the simulation, we need to have some material properties, so we'll leave it there. But later on, we'll be replacing everything. We'll create a separate material altogether. We are not going to use Ansys library. Okay, so we are good with material right now and geometry right now. In the connections, okay, in the connections we would expect to have contacts, okay, because we have multiple bodies. There are 8 bodies as we discussed. So why do not we see automatic contact generation? That actually typically happens with Ansys Workbench when there are multiple bodies. The reason is we created a new part out of it, and we use something called a shared topology. If you just revisit the video, you'll realize we created a shared topology wherein the planes and the nodes would be shared when there is an intersection, or there is a common plane between 2 bodies. The planes and the nodes would be shared, so the connections is already taken care of. So the software knows that, and it doesn't create any further contacts. One more thing, because there are no duplicate planes, so you don't have option to generate a contact as well, because in order to generate a contact, you need a contact surface and the target surface. And if you watch enough YouTube tutorials, you'd realize what I'm talking about. And since there is only a single plane between 2 bodies, no duplicate planes, okay, because the duplicate planes have been merged into a single one, and it now becomes an internal plane. Because they have been merged, you do not have 2 different planes to create a contact. Hence, there is no contacts over here. So the connections portion, we are good to go with. We do not need to create any connections. Okay, we don't have any connections. Ajay, by the way, let me just create a cylindrical coordinate system. Insert coordinate system. Cartesian. From Cartesian, I'll change it to cylindrical. And now, typically, Ansys would expect you would provide a geometry, and there is a body or a surface, and it would create the origin of the new coordinate system, be it cylindrical or Cartesian, at the centroid of that geometry, okay, which is the geometric center, right? So if it's a body, then it's a centroid of the volume. If it's a surface, then it's the centroid of the surface, and so on. But we would go with global coordinates, and the global coordinates being the global origin, that is 0, 0, 0. Okay, so we have now our cylindrical coordinate system, but look at the orientation of the cylindrical coordinate system. The orientation is not good. Okay, we would want the coordinate system to align its z axis, okay, along the axis of the specimen. Okay, so it is consistent with the axisymmetry of the problem that we have, that is the tensile test of a cylindrical specimen. So all the boundary conditions, all the loads, and the geometry itself all have an axial symmetric about a given axis. Okay, only when all of these are symmetric, the boundary conditions, the loads, and also the geometry itself, that's when we can claim a problem to be axisymmetric. So in this case, it's an axisymmetric problem. Okay, so what am I going to do? I'm going to change its z coordinate, okay, and align with the global x-axis. So yeah, so the problem that we wanted to solve has been solved here. So now the x direction represents the radial direction, y direction represents the theta direction, and z direction is of course the z direction, sorry, the x-axis, the axial direction of the specimen. Okay, so all of this have been fixed. So we are good with the coordinate system, we are good with the connections. In the mesh, I do not remember what is the best option, so I'm going to try a few. I'm starting with a multi-zone meshing option method, meshing method. So I'm selecting all the bodies, select all, apply, and I'm going with a multi-zone option. Okay, and I'm going to use element size. Should I use? If I use multi-zone, what happens? Okay, multi-zone meshing, and I'm going to use a element size. So if you are using multi-zone method, we'll have to have a fixed element size. So I'm selecting all the bodies. Okay, and I'm applying an element size. So this region is 30 millimeters, right? The testing region. So if I want to divide into 30 segments, so I should have an element size of 1 millimeter. Of course, here you cannot really change the units, and I believe the unit here is yeah, of course there is also a way to change the unit. So I'm going with millimeter ton. Why millimeter ton and not millimeter kg? Because that way megapascal becomes the unit of stress. Okay, and it's a consistent unit system. Once you take the unit of force to be Newton, and the distance is measured in millimeter, then ton is the consistent unit. Okay, with the unit of time being second. So ton, Newton, millimeter and second are consistent. Okay, whereas millimeter, kg, Newton and second are not consistent set of units. So I'm going with this one. Okay, and default element size is about 5 millimeters, but I'm going to use 1 millimeter, and I will choose to have element order to be linear. Okay, you would skip any higher order element. Okay, what is the reason for that? You will learn at the end of the at the finite element course that you would be having. Okay, so I'm going with linear elements, and let me mesh this region. Okay, multi-zone is supposed to be a smart sweep method. Okay, so multi-zone is where the software figures out what are the sweep methods. So there are different sweep directions. So one is the obvious sweep direction, is the axial direction. The other sweep direction is where you take a given quadrant. There are 8 quadrants, so you can take a given quadrant, and the sweeping is done in the along the angular direction. Okay, so from one plane to another plane. So for example, if I take this body and hide all other, so if I hide all other bodies, so look at this body. Okay, let me rotate this one bit. So consider this plane right here, and from this plane to this other plane there can be an angular sweep. Okay, that way the elements at the corner become wedge elements. Okay, wedge shaped elements, that is the like the slices of cake. Okay, that sort of element, and the rest of the elements are brick shaped elements, that is hexahedral element. Hexahedral meaning there are 6 planes. So so that is one sweeping direction. The other sweeping direction obviously is, let me do show all bodies, is of course along the axis. So let's just see what does the multi-zone method give us. It is supposed to give us a very good looking mesh, okay, but sometimes this method also messes up. Yeah, so this is what this is the axial sweeping. This is of course not radial sweeping. If you look at this surface, sorry, this is not angular sweeping, this is actually the axial sweeping that has happened, okay. So we can also work with this one, but if you look at this carefully, these two, this is a dog bone specimen, right? So it looks like a bone where the two ends are wider and the middle portion is thinner, and that is actually tensile region. And while undergoing the tensile process, that is the region that will undergo elastoplastic deformation, and that wider portion will have only elastic deformation. Okay, so there is no need for resolving that region, because not a lot of elongation is going to happen in that region. So there is no need for having that region being resolved with a huge number of elements. So you need majority of the elements in the middle. Okay, so if you are doing multi-zone, okay, probably it is not not the desired one, okay, but you can of course work with this one. So it is not giving us any sweeping behavior, not sweep size behavior, but it is not giving us any bias option, so that I can bias to have more elements at the center. Okay, so for that we can use a different method. So let me just suppress these two options. So now what we would do is we would just select one body out of the 8 bodies and create a mesh over there, and hopefully we'll be able to do an operation called mesh copy. So I've selected those two corner edges. Can you see that? These two corner edges I have selected. And here, these two edges are of the same size. Okay, because these are the radial lines, these are the radii. And I would like to have a specific number of divisions on this one. Okay, so instead of element size, I'm going with number of divisions. And the number of divisions I would prefer is anything between 5 to 7. So I'm going with 6. Okay, and because I'm resolving the radius with 6, okay, or if it helps if I if I'm resolving with 7, then probably I should resolve the circumferential line with 11. Okay, so can you tell me why I chose this to be 11? Again, I'm going with number of divisions and I'm selecting it to be 11. Okay, that way these 3 lines have the same nearly the same element size. Okay, acha, now I would be selecting this other edge. Okay, that is this edge right here. This edge I would select, and I'll provide a sizing. Okay, so I am providing a size over here uh, with number of divisions, insert sizing again with number of divisions, and I'm providing number of divisions to be, let's say I want to resolve this portion with 50 segments. Okay, now I want the element sizes here to be wider and here narrower, so I'm going to use a bias. Okay, first of all, any element size that you provide, you should set the option to be hard. Okay, so that it is, you know, strongly obeyed. And I'm going to use a bias, and that bias for me is something like this. Okay, hopefully this would work, wherein from left to right I would want it to be wider to narrower, and I'm using a bias factor of, let's say, 5. Hopefully that also works, but you see that has just, you know, reversed, so I'm going to use the reverse option. So here it is narrower and here it is wider, and how do I skip that? Just by going the reverse option. Okay, and accordingly also I would apply some other boundary conditions. So, sorry, not boundary conditions, but element sizes. So this corner, this edge right here, so here also, let's say if I go with how many divisions? If I go with 20 divisions, okay, and go with hard and provide bias. So the bias I'm selecting is once again this one, and here I'll provide a bias slightly smaller than this one, not 20 millimeter, but number of divisions to be 20. Okay, okay, probably I'll have to select this one. Okay, so what you can do is you can check whether this one and the other one is compatible. Okay, so probably you need to reduce the number of divisions on this one with number of divisions, let's say 15. Probably it looks similar. Okay, or maybe even you'll have to reduce the bias factor to 1.5. Okay, so here actually there are 3 edges. Okay, next is this one and this one. So here I have created number of divisions to be how many? To be 15. So I'm left with 35 more. Okay, so I'll have just the exact number of divisions together. Okay, over here. So I'm let me put another 10 over here. Or maybe not 10, maybe 7. Okay, this looks a bit similar to me. And then, so we have already used 15 plus 7, 22. So we are left with 13. So we can have 13 segments over here. No, sorry. So the total number of segments is 50. So 15 plus 7 is 22. So we are going to have 28 segments over here. Once again, I would like to use a bias. Okay. Okay. I think I need to increase the bias a bit. Okay. So to me, this looks like fine. Okay. Uh, so so now we'll generate. So we are done with element sizing right now. So we have totally given size to be, how many? 1, 2, 3, 4, 5, 6 edges, I believe. 6 edges. Okay. So now we are going to use sweep method. And for that we are selecting this body. Once again, when you are using a method, all the other options, that is vertex, edge or surface, would be turned off. Okay, so one body, and we are going with sweep method. Free face meshes should be quad and tri. Number of divisions. Okay, so number of divisions should be actually 11, because we are willing to do that thing. So yes, this element size that we have provided, we do not need this one. We can actually delete this one, because that's the direction we would be performing the sweep. Okay. Also, this edge sizing will only select this edge and this edge. Okay, uniform segments. So if I select all the edge sizing, that only applies to a given plane. Okay, so this would be our source face for the sweep method. So we have already selected the body. Now the source and target selection should be manual source, and you can also give manual target, but at this stage it is quite actually obvious. But let's just go with manual source, see what happens. So I'm selecting this face as the sweep face. Okay, one face has been selected. Why why are we going with quad and tri faces for free face mesh? Because you see, if we have hexahedral, sorry, once the angular sweep is done on this type of faces, on these type of faces we are going to have this face. At the corner we are going to have triangular elements. Okay, so let us just generate mesh and see what happens. Okay, measure failed, so clear generated data, and simply just click on this one and generate mesh on the selected bodies. Measure failed to initialize. Okay, so we change the sweep option to manual source and target, and along with the source face we also selected the target face, and that is this one. This is the source face and this is the target face. The source face and okay, target face. Okay, and with that we obtained the mesh for a single body. Okay, so if I show all bodies, okay, only one out of all the bodies have been meshed. Okay, why is it meshed? Let me clear generate data and only mesh this body. Yeah, so elements are created, and look at the elements. Okay, so this is how the elements are. So if you zoom in over here, you are going to see some wedge elements, wedge shaped elements, like the ones you obtained by slicing a cake. Okay, and later you'd have hexahedral elements, so you have rectangles over here. Okay, but if I hide all other bodies, okay, I get to see the interior. Okay, and it is not in this region, it is quite aligned. Okay, some misalignment is over here. Okay, so some corrections could be done. Okay, but at this stage it is also okay. This type of element is okay because our mostly the testing region is over here, so this is also okay. Okay, so now we will perform mesh copy. So this mesh copy is a powerful tool, and with that we have a very good looking mesh, at least from outside, on this one. So the basic mesh that we created on 1/8 segment, that has been copied everywhere else, and since this method works very well, we are going to delete the multi-zone and body sizing that has already been suppressed. At this stage I'll also save the file, and you can do it directly from the mechanical window. Okay, so now all we are done with, the majority of the pre-processing part is already done. The next thing that we need to do is to apply boundary conditions and set the analysis parameters. Okay, and what are analysis parameters? We'll talk about that now. Now we would apply the boundary conditions and set the analysis parameters. So for boundary conditions, let me first select the. So imagine the specimen is being held at the top and B is being pulled from the bottom. So the fixed crosshead is at the top and the moving crosshead is at the bottom. So for the fixed crosshead, this is what we are going to do. We are going to select the top 4 faces. Okay, so I would go with face selection, select the top 4 faces and insert displacement. Where is displacement? No. Insert displacement. Okay, and it would be fixed only in Z direction. So basically I am selecting that surface and constraining it along its normal. Okay, sorry, it should be constrained in X direction. Should it be in X direction? No. Yes, it should be in Z direction, but in the coordinate system that I have created. So I am going to call it, I'm going to rename it. So this is cylindrical coordinate system, or CLCS. Okay, so with respect to CLCS, okay, it is constrained in the Z direction. Okay, so you can also see the CLCS, so it is very apt over there. Okay, so this surface is being constrained from the top. Okay, now we would select these 4 faces. Okay, the 4 faces that are this one, and these 2, and we'll apply some boundary conditions here. Okay, again in the cylindrical coordinate system. And what boundary conditions are we applying? So imagine with the boundary condition about the axis, or the, so don't look at the the global Cartesian coordinate system anymore. All we are talking about with reference to the cylindrical coordinate system. So now it is only constrained, the specimen is only constrained so far, it is in the vertical direction, that is the Z axis, but it can still rotate about its own axis. So how do you prevent that? By preventing theta, which is here the Y axis. So I am just setting it to be 0. The other 2 is free. So similar to displacement 1, displacement 2, only one boundary condition is applied. Okay, we are applying no boundary condition in X direction, but X direction is here only the radial direction. Okay, so radially the specimen should be allowed to expand or compress. Okay, so as you elongate a specimen, it is supposed to have a lateral compression, and that lateral compression is only possible when the lateral surface, okay, or the surface is free from lateral constraint, which means you are pulling it along the axial direction, but its lateral surface is free to compress. That's how the lateral contraction can happen. So no constraint in X direction would be given. Okay, now again we would select these 4 surfaces, the bottom cylindrical surfaces with the wider portion, these 2 faces, and these 2 faces. You would insert displacement. Okay, this time the constraint is once again in the cylindrical coordinate system, all 3 boundary conditions in cylindrical coordinate system, but this time I'm not constraining it in theta direction, because that constraint is already given, okay, from the fixed crosshead. But even if you want to do that, you are free to do that. Okay, so even if you want to constrain along y-axis, you are free to do that, but it's not necessary, because anyway we are only going to be applying displacement loads, and all the displacement loads are along the axial direction. Okay, so you can set it to 0 or you can keep it free. Either way it doesn't matter. Okay, so now the next thing that I'm doing is I'm applying a displacement in z direction. Okay, so since the top, once again, this is all with reference to the cylindrical coordinate system. So once again, the top part is fixed by the fixed crosset. The moving crosset is pulling the bottom portion, and how much should we pull? So typical ductile material will elongate, let's say, about 20-25%, and in simulation it would probably go even further. Okay, so let's say we can expand up to extend the specimen up to 30% of its length. Okay, so that is what I'm anticipating. So I'm going with 30%, but 30% of what? Should we be taking from this corner to that corner? Actually, majority of this filleted portion that still remains in the elastic region, just like the wider portion. This what is it called? Chamfered portion. Yes, this chamfered portion or filleted portion, whatever you may want to call it. This the conical portion, that actually majority of the conical part actually remains within the elastic limit. Okay, so the part that actually counts is this uniform region. Okay, so 30% of this one, or maybe if you want to extend that, because this is kind of arbitrary, you can go with 50%, but I'll say that you can keep it to be 30%. Now how much is 30% of 30? About 9 millimeters, and I'm just going to put over here 10 millimeters, but it should be minus 10 because z-axis in the upward direction. So minus 10 millimeters is how much I'm pulling this one with. Okay, so with that we are done with boundary conditions. So what are the portions we have covered? We have the coordinate system, we have the geometry, we have the proper mesh, and we have the boundary conditions. And it is see, in finite element, the boundary condition should prevent rigid body motions. And rigid body degrees of freedom, how many are there? There are 6 rigid body degrees of freedom. So 3 translations, 3 rotations should be prevented. Okay, at least 3 translations, 3 rotations. Now if you look at it, at the top surface there is a constraint about z-axis, which means this specimen cannot move along z-axis. That is one constraint. But if you fix the top surface about entirely, the entire top surface about z-axis, it cannot also perform rotation about x or the so-called y-axis. Okay, so that actually 3 constraints in one go. Okay, that actually is 3 constraints. Okay, now on these 4 faces you have constraint about theta direction, but the theta direction keeps on changing. Sometimes it aligns itself with x-axis, sometimes it aligns with the y-axis. Okay, so it is a constraint in both. So there are 5 constraints already there. Okay, also it is preventing the motion, since it is on the entire surface. Okay, it is also preventing the rotation. So it's a constraint in theta direction, so it is also preventing the rotation about z-axis. All the 6 constraints are literally over here on the top top 8 surface. You have given all the constraints. Okay, on the bottom 8 surface you are only applying the load. So you are kind of over constraining the problem, because yes, it is over constrained, because it is going to deform. It is not going to have a rigid body motion, it is going to deform because of this over constraint. So it is, in a way you can say, it's a statically indeterminate problem. Okay, so done with boundary conditions. Now we are going to look at the analysis settings. Okay, so now we have entered into analysis settings, and the first thing that we check, that weak springs are off. Okay, so what are weak springs? Weak springs are there for full proofing, FOOL, full proofing. It's because if you forget to provide any rigid body constraint in a direction where there is no force, okay, because in finite element method, even if there is no force in a given direction, you still need to have a rigid body constraint for the object in the same direction, and that applies to both translational and rotational degrees of freedom. Okay, otherwise mathematically it cannot solve the problem, because the zero force can yield an arbitrary amount of deformation, okay, in a given direction. So weak springs can take care of that in case that constraint is not there. But if you have properly constrained the problem like we have, then you should skip the weak springs. Okay, so that minimizes the error in your solution. Okay, does that make sense? Okay, next thing is we are going to do an elastoplastic analysis, okay, which means the strain here is going to be more than 1 in 1000, okay. So once again we are considering metallic materials, and in metallic materials the elastic strain or the elastic limit in terms of strain is about 1 in 1000. By the time a 1 meter length metallic rod has had an elongation of 1 millimeter, it has already entered into, it has already yielded and already started having plastic deformations, okay. So see, when the material is only deforming elastically, you don't have to have large deformation turned on. But if it is beyond that, okay, if it is beyond the elastic limit, if we do anticipate having elastoplastic deformation, like here we are expecting a 30% deformation, more than 30% deformation, as we discussed, 10 millimeter elongation. So there, large deformation should be turned on. Also, plasticity is material nonlinearity, which would already bring in Newton-Raphson iterations. So we are no longer within the domains of linear finite element analysis, okay. The moment we choose elastoplastic material model, we will have to have nonlinear finite element analysis. So it is better to have large deformation turned on for better accuracy, because once again we are dealing with strain, okay, dealing with large strains, right? What is large strains? So in your undergrad you may have studied true strain and engineering strain, that is logarithmic strain and engineering strain. So when the strain is of the order of several percent, let's say 5, 10, 15%, then the logarithmic strain or true strain deviates considerably from the engineering strain, and that's the region we are talking about. Hence the large deformation should be turned on, okay. No other setting in this part, the solver control needs to be turned on, but you directly go into number of substeps, okay. So step n time, why are we talking about time? Although we are solving static analysis, here we bring in the concept of time, which is actually something called a pseudo time, okay. It's not the officially what it is called, but that's what it is supposed to be known as, because we this time actually gives us a sense of what portion of the load has been applied. For example, if you are applying 10 millimeters of deformation, that would be applied in a time span of 1 millimeter, okay. This is not a real time, okay, and this doesn't really contribute to the strain rate, okay, because you know we are looking forward to applying a rate independent plasticity model, okay. So we are going to be doing a rate independent plasticity model. We are not going to do any viscoplasticity or any rate dependent plasticity, where the strain rate has a effect on the stress value. So in this case, this time is only there for an indication of the load level. So if you apply 10 millimeters of deformation in 1 second, in 1/10 of a second you apply 1 millimeter of deformation. That's what this means. And we need to change the time stepping. We would turn on the time stepping on, and since we are doing elastoplastic analysis, okay, this is what I would suggest. You see, we are talking about 30% of the strain, okay, that is 0.3, okay, and the elastic region is only 10 to the power minus 3, that is 1 by 300 of that, okay, 1 by 300 of that. So so if you want to have more than one solution point within the elastic limit, okay, you need to have, initially at least you should have 1000 substeps, and that would also be our maximum number of substeps, okay. And minimum number of substeps should be it should be at least 50, because but we are resolving a maximum strain of 30%, so I'm going with 100, okay. So initial number of substeps 1000 would ensure that between 0.1% of strain you have about 2 or 3 substeps, 2 or 3 solutions. So even within the elastic limit you will have more than one solved step, okay. That actually is increases the accuracy of the solution. Also it avoids the unnecessary bisection of the steps, because when the yielding happens, because the the material stiffness abruptly changes, and I do put emphasis on the word abruptly because it does. When the stiffness abruptly changes, the solver has to take multiple steps to resolve that. Okay, and you can imagine the yielding happens at the end of the elastic limit. So you need more than one step to do that. So it is better to have more than one sub-step within the elastic limit. Okay, so that's why I'm going with 1000 steps, 1000 number of initial substeps. So the smallest time step size would be 10 to the power minus 3, and the largest time step size should be 10 to the power minus 2. That's what this means. Okay, so don't think of in terms of substeps. It is actually an indication of the smallest time step size and the largest time step size. Okay, so we are good with anything that we need to do with the analysis part. Okay, maybe we need to look at the output control, but I believe for a static analysis every required solution is already set to yes. Okay, and we can right away hit the solution. Okay, and we can do the solution and look at the results. But remember, we only have a linear elastic material model here, so from this point onward we need to set the proper material model and then perform the solution. Since we do not have any experimental data for the day, what I'm doing here is I'm going through a PG thesis and I'm collecting some of the material parameters from there, and in the next class we will discuss about how to extract those parameters and incorporate them in the workbench engineering data. So as we discussed that in workbench we would create a new material model, and I'm going with this one, the third one, UHSS heated. Okay, for which I have been given the Young's modulus. I've been given the Young's modulus, and these are the parameters that have been given. This K right here is the yield stress. This 209 is the yield stress. Okay, so how to obtain these values, okay, we'll discuss about that in the next class. So I'll provide you with a MATLAB code, okay, or I'll show you how to write a MATLAB code that can actually give you those material parameters. So so once we do the experiment we'll have the material data, but right now we don't have any. So and these are the parameters, the third table. Okay, we'll take. So this third table will take. Okay, so we have two Chaboche term. Each Chaboche term will have two parameters, C1 and gamma 1 for the first term, and C2 and gamma 2 for the second term. Okay, so we need the Young's modulus. Poisson's ratio we can provide it to be, let's say we can take it to be 0.3 for that matter. This is the yield stress, next parameter, and then these are the Chaboche parameters that we are going to use. These are the parameters we are taking. Okay, so here we are creating a new material model. Okay, and that is what we are going to use in the simulation. Okay, so right now it shows a question mark because no other property has been given. So I'm going with linear elastic. Okay, and you can have anisotropy, orthotropy, or isotropic elasticity, but I'm going with isotropic elasticity. Okay, so it is asking me about the Young's modulus, so I should have it set in the proper unit. So I'm selecting GPA, and in this thesis the value has been given, okay, to be 152.28. so I'm using that value. Okay, and next I'm using the Poisson's ratio. I'm taking it to be 0.3. At this stage it doesn't really matter. Okay, and once again you can save the project right here. Okay, once again if you click on UHSS it will show you more properties. So it is now asking for so we now provide plasticity model, but don't go with Chaboche test data. That is where it fits the Chaboche model from the Chaboche test data, but we are going with all the fitting we will do in our own way, and we will provide the Chaboche kinematic hardening. Why are we using kinematic hardening, and what is kinematic hardening? Actually there are two types of hardening. So what is hardening? To understand hardening, let's draw some diagrams. So okay, so typically with metallic materials, let's say this is the strain axis and this is the strain axis, and I'm not putting any unit. Okay, so the initial part is this straight line which has a slope of Young's modulus 1:E. Okay, uh, okay, and and so when it encounters the yield stress sigma y, okay, so after that uh, there is still some slope left, right? So it doesn't simply become flat, the slope is greatly reduced, okay, abruptly changes, but it doesn't become zero. So this slope, okay, this part is called hardening. This is called strain hardening. Okay. Now this hardening may result in two different ways. One is that once you unload, sorry. So once you unload, okay, it comes, it follows the initial slope. So that is the slope of the elastic region, okay, and that way the range of the elastic region increases. So once it unloads, it goes over here, follows this line, but once it reloads, it still follows this line, and that way you have when you yield it for the second time, the yield stress now increases, okay, and that increment is called the hardening stress. Okay, let's denote that with x. This hardening stress is denoted by, let's say, x. But instead of reloading, if you load it in compression, two things can happen. One is that it yields at a stress value of sigma y plus x. So now that it's tensile yield stress, okay, tensile yield stress has increased, okay, so now it could yield at this, increased yield stress, or it can yield at sigma y minus x, that is over here, sigma y minus x. Okay, so it could be yielding over here, or it could be yielding over the higher stress. So if it yields at sigma y minus x, then this region where the material remains elastic, going from tensile to compressive, this region has a fixed length. Whether you are yielding for the first time or the second time or the third time, it has the fixed length, and that length is twice sigma y. Okay, so if the yielding occurs at sigma y plus x, it is called isotropic hardening. That is, the yield stress in tension matches the yield stress in compression. And if the yielding happens at sigma y minus x, it is called kinematic hardening. That is, tensile hardening increases the yield stress in tension but reduces the yield stress in compression by the same amount. That is known as kinematic hardening. What this basically means is the origin in terms of stress has shifted by an amount of x. Okay, so that origin, the midpoint, has shifted in terms of x. Okay, so that's what is kinematic hardening, and kinematic hardening is is basically manifested by this shift of origin, and this x then is called the back stress. Okay, typically a real material will have a combination of both isotropic and kinematic hardening, and the yielding in compression for this scenario would be somewhere between sigma y minus x and sigma y plus x. It is not purely isotropic or purely kinematic, but here we are going with purely kinematic hardening, because typically that is the more dominant effect, and this is also known as Boschinger effect. Okay, so if you want to know more about it, go to the internet and study about Boschinger effect. That is something a postgraduate student should know, studying the material behavior. Okay. Okay, so this type of material model is the Chaboche kinematic hardening, and for those parameters you would be incorporating. So Chaboche terms, now it would be asking how many Chaboche terms do I want. I would say I would want 2, and all the parameter values I will set to megapascal. Now it will need the yield stress, it will need the C1 parameter and C2 parameter will have units. The gamma 1 and gamma 2 parameters, in this case y1 and y2 parameter, they are dimensionless. Okay, they are basically scaling parameters, so they are dimensionless. So if I go to this PDF, I can see the yield stress. This K right here is the yield stress, is 209.03. So I'm going to incorporate that in megapascal, of course. Okay, and then the C1 and gamma 1 values are this, 57654. So I'm just putting it towards this left and this one towards the right. Okay, so this one is 57654. This one is 520.94. This one is 2815.7, and this one is 14.796. I'm only taking five significant digits. Okay, so we have incorporated our material model. We'll save it, but that doesn't ensure that this material model will show in the mechanical window. For that, what we'll have to do is we'll have to do a material refresh, and once we do that, this material is now being shown. So it has its yield stress, it has its Chaboche parameter. Any plasticity model that you use will always ask you for the yield stress value. Okay, so it should know when to stop the purely elastic calculations. Okay, so the software must know where it should stop that. And the C1, gamma 1, C2, gamma 2 parameters you have incorporated. Now we need to assign this material model through this geometry. So for all the parts over here, I would change the material model to UHSS heated. Okay, so if you look at individual bodies, okay, they will all have this material model. Okay, so we are good with the material as well. At this point, once again, save your file. Okay, and now we are good to go with solution, and post solution we'll look into whatever outcomes we obtained. So now we will solve this one. Okay, and while it solves, we'd look into something called force convergence. So this blue line or the cyan line is actually the solution criteria, and this purple line actually shows the force convergence value. Basically, in nonlinear finite element method, there is a residual of the externally applied force and the internally developed force that is due to the stress development. Okay, and the residual of the two, that is the difference between the two, must remain a certain norm, and this is the norm in Newton. This is the norm. This blue line is the norm, and purple line is the sorry, this must lie below certain tolerance. So this blue line is the tolerance, and this purple line is the norm of the force values. Okay, so you unidirectionalize that force value. Basically, you take the dot product of the force vector with itself and then take the square root. Now this is the value that so you can see the iteration started happening. So always the steps were converging in a single step. So these are all the sub-steps. These green lines represent converged sub-steps, and initially the convergence was occurring each step. And after, let's say, this fourth converged step, iteration started happening. So the force norm went outside of the tolerance limit, and then it converged back. And then it happened for quite a few times. This is where actually the yielding is happening. Okay, and that's why the slope of the stress strain diagram changes abruptly, and therefore the stiffness of the structure changes, and hence the iterations need to be quite a large number of iterations. Not quite a large, but some iterations must be done over there. But after a few iterations, of course, the steps started converging at single step. Okay, so now if you look at the time increment, okay, initially it started with 10 to the power minus 3, and then it kept on increasing, and at most it went to 10 to the power minus 2. Okay. You see initially that you had in force convergence, you see this 3-4 steps that happened before yielding. Okay, that is only because we took the initial number of sub-steps to be 1000, or initial time step size to be 10 to the power minus 3. Okay, so that is only what is giving us, you know, solution points within the elastic limit. Okay, now we have already converged about 80% of the solution. So as I said, this time only is an indication of the, you know, the load level or how much the solution has converged. So it has converged only about 20%. Okay, and it will take time because, you know, it is taking an increment of 1 in 100 second. Okay, so it will probably take 5-10 minutes to solve. Let me check whether displacement converges in on. Yes, the displacement converges is on, but since we have properly constrained all the rigid body motion, we could have actually turned off the displacement constraint, and you can do that from over here in analysis settings. In nonlinear control, there is force convergence as well as displacement convergence. You could also turn off displacement convergence in this case. You don't need that because the force convergence has the upper hand over here. So wherever this thing went outside of the tolerance, once again here is a tolerance, the force convergence also went outside of the tolerance, and in this problem where the problem is where the, you know, the geometry is quite the constraint has been proper. Okay, that you have restricted all the rigid body motions, you don't have to have displacement convergence on. Okay, so only quite a few analysis settings should be, you know, looked at. Okay, although there are problems in which we must look into, you know, many of these. Okay, including restart control and whatnot, but for this particular problem you don't need as many. Okay, so I've already converged about 30% of the solution. So you can imagine you have applied a displacement of 10 millimeters. So around 3.3 millimeter has already been applied. Okay. So while the solution is on the go, if you want to see the you know, the incomplete solutions also, you can do this displacement solution tracker and, you know, insert stress plot tracker. For stress, I'm going with equivalent von Mises stress. For deformation, I'm going with total deformation for the time being. And for both of this, I'll select auto update. So these are the trackers. There is only a few options, but you can still track the solution even before the solution has been completely converged. Okay. Now you can see this force convergence curve, you know, initially went below, well within the, you know, the tolerance limit, but suddenly started rising. And this rise there is because this portion was yielding portion. Now you are encountering the ultimate stress. So you are encountering the yielding region. Now you are encountering the ultimate stress point. Okay, but we would be able to simulate the ultimate stress points because it's a displacement convergence solution. That means all we have applied is displacement. We have not applied any force. The force is the response to the displacement. Okay, so once the solution is complete, we would be using a probe to track the reactions as well. But right now I believe it is encountering ultimate stress. So necking should start forming now. Okay, so I want to get rid of the elements, but I want to show the undeformed wireframe. Okay, so so as you can see, or yeah, so as you can see, this line represents the undeformed geometry, and this shaded area, that is the deformed geometry. If you look closely, it is having the lateral contraction. Okay, and it is having this much of elongation, and in the middle region, you know, you are already approaching the stress value where the necking must happen. Okay, but it will probably take some more iterations before the necking to happen. or I believe the necking has already started. If you zoom over here, you'll realize some sort of necking is already happening. Can you see that? Tensile test je necking hoy amader seta hocche ekhane. Okay, and that neck is gradually becoming narrower and narrower, and because it's a simulation and we are using a material model that is suited for ductile materials, we'll have the perfect ductile material behavior, which means the neck actually contracts enough to touch itself, touch the other side of itself. Okay, so right now the deformation has been about 52%. Okay, the solution of around completes by 53-54%, and if you look at the stress value, so remember 209 was the yield stress. We have already reached this much of stress. Now remember, this is only the stress in the in the neck. Okay, and and that is about 510 megapascal to 450 megapascal, that much of stress. But if you multiply that with the cross section area of the neck, that is not a huge force value. Okay, so although the true stress is quite high, this actually shows the true stress. Okay, it takes into account the the change of the geometry. If the large deflection had not been turned on over here, okay, it would not be showing the true stress. You would be getting the engineering stress, but right now you are getting the true stress. Okay, and the engineering stress on the other hand would be far lower. Okay, because the cross section itself is much lower. So we'll let this simulation complete, and this only going to progress. So our solution have already converged up to 95%. If you look here carefully, the reason why we took fine mesh in the middle now the elements have been greatly stretched. Particularly the elements that are exactly connected to the middle plane, they are stretched the maximum. Okay, and if this thing continues, even for further elongation, okay, we have taken at most of 10 millimeters of elongation. If it still continues, okay, it will keep on increasing. Okay, and if you see carefully now, in this region there is no typically the element size is actually higher closer to the neck compared to at a distance. Okay, so that has happened because of stretching, and to have that thing being accounted, okay, or further to look at this necking behavior more accurately, you probably need a finer and finer mesh over here. So we now probably having around, yeah, we had started having bisections. So basically now we have a limit where it can no longer take any further load. Okay, so it would probably, so since bisections are happening, you would see the time step size has started decreasing, and if it falls below 10 to the power minus 3, it will actually stop solving, and we will probably have an unconverged solution. So that 10 millimeter elongation that we gave, that was actually too much apparently. These are the iteration numbers, cumulative number of iteration 175. Okay, and earlier it were taking, let's say, 1 or 2 iterations to converge a substep. These green lines are converged substeps. These red lines, so as the steps comfortably converge, the solver is smart enough to increase the time step size. Okay, and as the solver faces an issue in convergence, okay, so let's say not only the tolerance is the norm is higher than the tolerance, okay, it also kind of diverging, then it takes a bisection, which means it reduces the time step size by 1/2. Okay, and then then maybe it will converge, Okay, and at times, you know, with several number of iterations, they do not converge, and with multiple bisections happen, and the time step size falls below the lower limit. Currently, it is at the lower limit. If any further bisection happens, okay, the solution would be stopped. So if there is a difficulty in convergence, there would be bisection and time step size will increase. If there is an easy convergence, okay, say 1, 2, 3 iterations or even 5 iterations, okay, consecutive convergence after convergence, then the time step size will increase. Okay, it will increase in a multiple of 1.5, and it will decrease in a fraction of 0.5. Okay, so the amount of increment and amount of decrement is the same. So as you can see, it has finally diverged. Okay, so even for unconverged solution, we can have solutions. For example, I already know how I applied the deformation. Okay, so but this is what I am going to do. I am going to get the directional deformation. In what direction? In x direction, in global x axis. Okay, of which 2 points? So for example, in an actual experiment, you will be connecting an extensometer, and that extensometer would actually measure the distance along x axis for 2 different points. Okay, difference in elongation. Okay, so I am choosing this particular vertex and the top one right here, okay, and applying. So only for these 2 vertices I am checking the directional deformation. So if I evaluate this result, okay, so you would see I don't need the average value. The minimum one, the green line, actually shows the deformation of the top point. Okay, so the top point is actually closer to the fixed crosshead. Okay, so this top point deforms by this green line, and this red line represents this blue point. Okay, the lower point that is actually connected with the moving crosshead, and actually that is the one having the higher amount of deformation. Okay, so we'll take it up to the last converged substep, that is 0.97133. Okay, we'll take that one, and we need these two to measure the strain across the engineering strain across that 30 millimeter length. So if I take the difference of this green line and the red line and divide by 30, I have the engineering strain. Okay, for that 30 millimeter length, you can consider that to be the gauge length. And we can also have a probe, something called a probe. Okay, and this probe will give us the force reaction, and I can connect it to either to so look at the displacement that I have applied. This is the displacement, the first displacement I have applied, which constrain the motion in x direction, or the z direction for the cylindrical coordinate system. So if I connect to that one, it will give me the force. Okay, so if I select the first displacement, that will do the job, or if I select the third one, which actually pulls it in the downward direction, that will also do the job. Okay, so let me just select the third one. Okay, and if I evaluate this one, okay, that actually shows a plot which kind of looks like this. So this is the linear elastic part. Okay, force reaction. I only need the one in z direction. I only need the one in the x direction. If you compare the values, this is the value in x direction, this is the value in y direction, this is the value in z direction. In y and z, you will see a very small value of the order of 10 to the power minus 8 Newton. These are actually numerical error. Please understand, you are doing a nonlinear solution where iterations are involved. All the solutions that you are getting are numerical solution and bound to have error. So this is not perfectly zero, it has some small value. Okay, so I only need this x value, nothing else is required. I don't need the resultant or anything. I only need the x value. So I'll collect this one. Okay, and I'll collect this one, divide that with the, if I divide this with the original cross section area, I'll have the engineering stress diagram, engineering stress values, and if I can get the engineering stresses and engineering strains, and I can plot these two to get my engineering stress strain diagram. And once we do the experiment and once we do the simulation, we can compare the experimental engineering stress strain diagram and the simulation stress strain diagram we can compare. Okay. By the way, we can actually evaluate the ultimate stress, and the ultimate stress would be this number, this much Newton, that is around 12 kilonewton, 12 kilonewton divided by the cross section area. So we have taken, so this is 11920 Newton divided by pi, and then divided by uh, 3 and divided by 3. So this is going to be our ultimate stress. So what are 3's are there for? So you see it is uh, pi r squared. So if 6 millimeter is the diameter, 3 millimeter is the radius. So if I divide 12 kilonewton by this much millimeter squared area, so this in megapascal 421 is going to be our ultimate stress. Okay, and over here I don't know how much ultimate stress we have gotten. So this is what probably experimentally was obtained, 423 or something. Okay, so this one is very close to that one. Okay, so your job while doing both the experiment and the simulation should be match the ultimate stress values and also match the experimental stress strain diagram with the simulation stress strain diagram, or if they do not match, comment on that. Okay, so that's all we will be doing in the next class. So I think we are done for today's class.